All right. So where was I? All right. Well, welcome everybody. Today we're going to talk about NFTs and how to program them with Fluence and Aqua. And since this is the shelling, misspelled hackathon, for those of you not aware, focal points are not necessarily a big deal, but an important part of game theory. And non-communicative coordination is actually a big deal, and we encounter it everywhere. So setting up making it a shelling themed hackathon is really, really cool. And if you look in the blockchain and Web3 ecosystem, there are a lot of focal points, a lot of shelling points that over the past few years have sort of emerged. And usually individually without coordination, different camps, different people, different minds arrive at some pretty interesting solutions. And right now in the NFT space, some of those emerging shelling points or focal points are literally cross and multi-chain NFTs. By cross-chain, we are looking at NFTs that are bridge between chains, and by multi-chains, we're looking where we use front ends, centralized to decentralized, to manage NFTs across multiple chains. Who's going to win? Who's going to lose? Hard to say. I don't know if that's going to be a VHS or Betamax, or maybe both fulcrums will survive and grow and prosper. We'll see. But right now, these are emerging shelling points in the ecosystem, and also very, very relevant. And our bounties are built around NFTs. I'll go through them at the end, but basically everything in the workshop I'm trying to do is trying to basically enable you to be successful as much as possible and succeed. And yes, if you're a beginner, stick around, either find a team or you know, get inspired sufficiently to dig in. Okay, so decentralization is a really big deal. I think if you're coming from Web3, it's really important, and particularly the Web3 aspect of how to look at decentralization is really important. It's important because this is where you can start fighting certain things like loss of control over your data, and many other privacy invasions. And that's where peer-to-peer platforms comes in. You can do decentralization in many different ways. However, only with peer-to-peer networks, you really get the full benefits of the attributes of Web3, including censorship resistance. And this is where Fluence comes in. Fluence is basically, it's a peer-to-peer development stack and a bunch of tooling that allows you to okay, the drawing is throwing me off there for a second. That allows you to build decentralized protocols and applications. And the Fluence stack itself, the protocol itself, is all about compute, decentralized peer-to-peer enabled compute. And so as a developer, you have to bring alternative data solutions to the place, including which should be decentralized, such as IPFS. And if you look at it from a sort of a bird's eye view perspective, peer-to-peer networks, which are on the right, this sort of a very small one, you basically have clients, and then you have peers that communicate with each other. Those are your peers in the network. And the relay, just to make sure everybody's on the same page, a relay is a peer that sits in front of otherwise non-accessible peers, which could be behind a NAT, which could be behind a firewall, which could be behind or could be preemptively prevent you from connecting directly through various censorship interventions, and on it goes. So the big deal about peer-to-peer on the Fluence side is that it's a general purpose peer-to-peer network and protocol. For those of you that have been in the Web3 space, you've probably been either directly or indirectly, encountering peer-to-peer networks as part of blockchain. Blockchain is probably the biggest rejuvenation of and evolution of peer-to-peer technology. And in blockchains, Ethereum, for example, peer-to-peer is used to communicate, to find other nodes, and then to sync data across nodes. And that's where the decentralization comes in through peer-to-peer on most of the blockchains. IPFS, you do the same thing on the data level through content addressable IDs. And the old big P2P applications usually are the Napsters. So it was always about data. And one of the things where Fluence is different is it gives you compute. So if you really, really need an analogy from the Web2 space or from an alternative space, is you can think of it of decentralized serverless. So decentralized Lambda at the roughly at the highest level. That's what decentralized compute gives you. So if you look at the network, this illustrative network over there, so you have these peers, and then you deploy business logic, which we call a service, onto those peers. And that business logic is written in as WebAssembly modules. And it's actually WebAssembly interface types, not WebAssembly bindgen, which you usually find in front-end development. So if you start thinking through this, so you get these bunch of peers, you somehow end up hosting these WebAssembly modules, which are addressable through a service as a service. And then you can start sort of building workflows that basically give you the logic on how to execute these services. Now, we understand that not everything is going to be on the Fluence network, which actually, by the way, is open, permissionless, and all the tools are open source, Apache 2 or MIT, so it's very permissive. But what you can do is you can actually take those services and write adapters for already existing solutions like APIs, microservices, or other peer-to-peer plays like IPFS. So if you're looking at this, so you get the green ones are clients, which could be a browser, which, by the way, is a very important entry point. It could be an edge device. So in peer-to-peer, in proper peer-to-peer networks, your client can be very, very thin, which is really, really important if you want to scale and minimize your onboarding through clients. So those two green things could be a browser, and browsers can't directly connect to be a node in the network, so they would have to go through a relay. And so if we have a couple of services, I don't know, let's just say you want to send a text or a message from the upper left one to the lower left one browser, like a chat, for example, and you want to have like one service could be I don't know, spell checking. The other one could be ASCII to emoji conversions, for example. Then what you do is you package up, and this is all taken care of for you. You package up your message, you send it to your services. They do the markup, the spell check, whatever you want to do. They turn your ASCII into emojis, and then it gets delivered. So that, of course, it sounds very easy. It actually is not, but a lot of the work is taken care, is black box for you, so you don't really have to dig very, very deep. The big deal, or the big question should be at this point is how do you actually get to that service? I mean, I'm here in my browser. How do I get there? And it's peer-to-peer, so you don't, in our model, in the Fluence model, you do not use REST endpoints or JSON RPC. You actually use a different kind of addressability model that is comprised of a peer ID and service ID. So a peer ID is actually just a hash of the public key of the node operator. So the peer ID is actually not related to the IP address, which has a lot of advantages, but also disadvantages. There are security risks because of that. And we have a lot of the, well, not a lot, all of the security requirements to stave off the majority, actually most majority of all the possible Sybil, Eclipse, blah, blah, blah attacks you could possibly get. Because one thing you can do is if the addressability is on a peer ID, not the IP address, on a single IP address, you could quote unquote run, a very large number of phantom peers, and those could be attacks. But there are ways to mitigate those attacks, and they are in place. So if you can't use REST or JSON RPC, how do you actually how do you address those services? As I said, you address them by peer ID, and services have a unique ID, and you use Aqua. Aqua is a programming language and development stack developed by Fluence, and it's a fully dedicated, purpose-built peer-to-peer programming language. And it's super simple, and we'll go through all of this because that's what you really need to do. That's really what you need to see in order to be successful in your hackathon endeavors. And so let's just go forward. So we have two big stacks that are part of every node. It's Aqua and it's Marine. Marine is a general purpose runtime environment for WebAssembly modules. As said, services are coded as WebAssembly modules, and Marine actually executes those modules. Aqua is the programming language and part of and the compiler, and it also includes a virtual machine. It's called the AVM, the Aqua Virtual Machines, and that actually executes the compiled Aqua scripts. And they're available on every peer. And we go through exactly how this works in a split second. So basically what that enables you to do is that it enables you to separate your business logic, your services, from the actual topology required to discover services through the network. That's where Aqua comes in. And that's what actually enables peer-to-peer applications. On top of it, if you're into zero trust type frameworks and environments, it's inherent in the way the system is built, because, hang on, where's my brown? Here it is. Because at every ingress and egress, there are signatures collected, and that allow you to actually validate exactly what has happened on every state change. And so this actually fully enables the zero trust architecture. And then it allows you to actually collaborate and compose over peer-to-peer networks, a variety of protocols and applications. And if we go back to the network, stylized network, so we had this message we were going to send, and we're going to mark it up. So the data goes somewhere through the network. It discovers the service does a state change, fix all your spelling mistakes. Then we said we wanted to turn it into emojis, and we're do another discovery for that emoji service, and you get another state change, and then it goes back here. So basically, if you look at it, in traditional client servers, what you would do is you would go from the client to the service, back to the client, to the service, back to the client, and then to the recipient. That's not what's happening at all. And what we're doing basically is we're pushing a data model or a smart package. We call it a particle. And particles are conflict-free replication data structures that combine data, so your message, for example, to the anticipated recipient, as well as the recipient address, and the execution sequence. That is your compiled Aqua script. So this compiled, you can think of it as bytecode. It's not bytecode, it's actually a Lisp-like output that comes from compiling it, and we call it AIR, Aqua Intermediate Representation. But that is part of that smart package packet of that particle that gets flung onto the network. And it literally is what's happening here. You create this initial particle at the client, and then you sort of fling it onto the network, and then the Aqua virtual machine starts looking where it is in the execution script and where it needs to go. And this happens at every hop. So what you get here is this, the particles are the little green things up here. What you get here is it's basically these particles, they hop from addressed service to addressed service all the way until the end of the execution script. And this is what particles do. And this is where a very unique but extremely effective programming model for change and general compute. And as I said, the important part is it's general compute protocol that allows you to basically do anything and basically decentralize anything you would want to decentralize. Okay, let me just look at the chat here. Anybody has any questions? This would be a good time. Okay, so Fluence is not a blockchain at all. Fluence is, come on, go away. Fluence is an off-chain, environment where we provide the bootstrap to a peer-to-peer network. We provide reference nodes or peers for a network to join an open permissionless network. So in a blockchain, the way, I mean, there are a lot of aspects to blockchain, but basically what happens is you create some transaction. A transaction gets processed through the miner. It gets put into the block, and then every node in the blockchain system reruns those transactions. And if they're validated by each and every one, you get the longest chain, and the longest chain wins. And this is how blockchain works. In Fluence, you don't rerun. So the downside of blockchain is the way it works. If you add additional nodes to the network, you do not essentially add scalability. What you add is more security. The more nodes you have, the better you are equipped to fight off Byzantine attacks. In Fluence, this is not the case at all. What happens in Fluence is each node operates independently. However, as you execute your workflow, you end up with a log, if you will, that actually contains a whole bunch of signed messages which actually make up a proof. So you can rerun, if you want to, the execution of that workflow through the various stages of the particle processing, where each stage is, of course, the state change, and verify that. And so what basically happens is you're putting your consensus, if you will, at the application level rather than the network level, but you put your scale of the network directly proportional to the addition of new nodes. Yes. Okay, so yes, there are additional resources, and somehow I'm stuck on this stupid little thing. And I will go through them. All the documentation is on fluence.dev, and that's where Fluence references and Aqua. But we'll go through Aqua. Actually, a big chunk of the remaining presentation or workshop is all about Aqua. So before we go to Aqua, I want to sort of quickly go through the tooling in a nutshell. So we have a Rust SDK. The WebAssembly modules you're building in order to create services are coded in Rust. So before you just throw up your hands and say, I don't want to ever touch it, it's the easy parts of Rust. If you know JavaScript, if you know Python, whatever, you should have no problem, because all the difficult stuff that comes with Rust, lifetimes, generics, blah, 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 none of that applies. So literally the first 4 chapters in the Rust book is all you need, because in WebAssembly, everything's passed by value. And so basically what you're doing is you write these services in Rust and compile them into WebAssembly modules. And then you link these WebAssembly modules into services. So services actually are virtual constructs based on actual WebAssembly modules. So if, for example, you want to have a service that calls out and does some HTTP calls, requests. I don't know, like for example, some of the directly interacting with an Ethereum node, for example, or an EVM, whatever it is, using JSON RPC, then you would have two WebAssembly modules. One is the actual adapter to curl, and I get to this in a minute, your HTTP adapter, and then one would be the business logic. And then you have a JSON file that links those two modules into a service. So basically the modularity of the service construct is such that you actually can reuse and repurpose those modules depending on the granularity you've used to create these services very, very efficiently and effectively into many different configurations. Why curl? So WebAssembly IT is extremely safe. It's extremely secure. And a lot of it has to do is that it's fundamentally sandboxed, which means that those WebAssembly modules natively have no access to host resources. And that's where the security model comes in. So what we've done is we sort of, quote unquote, pierce the veil of the sandbox through permissioning, that by permission, the WebAssembly module may access host resources. Why does that matter? Well, for those of you who've been following WebAssembly modules are single-threaded and fundamentally have no sockets. So in order to be able to particularly on the socket side, in order to be able to actually interact with the outside world, you somehow need to be able to do that. And one way to do that is to, for example, access HTTP request resources provided by the host, the node, the peer. And curl is one of those resources. So basically you can do, quote unquote, a binary mount into the WebAssembly modules and then take advantage of what the host is providing. And as I said, that's permission-based. And this is how you create, so basically different modules, WebAssembly modules can be configured into different services. There is basically every configuration of WebAssembly modules into a service is reflected by a unique hash. It's called a blueprint ID. And then you can associate unique service IDs to those blueprint IDs. And the reason you do this is because actually with Aqua, you can parallelize your workflow or parts of your workflow. So if you wanted to run, for example, service instantiations, multiple service instantiation on the same node, you would use the same blueprint and the resources, but the instantiation would come through different service IDs. So you actually can, because it's about addressability now, not just the reuse of the resource. Or you could obviously do this across different peers. So then depending on how the hosts are configured in terms of CPU, RAM, blah, 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 you can also parallelize across the network, which is actually really, really powerful. In addition, what the Rust SDK provides you with is some really, really good testing. Why is that important? Fundamentally, if you do unit integration tests, you do it on your code, right? You write your Rust code or whatever, and then you run the unit tests on the code. And that's nice, but our compile target is actually WASI-32 WASM, which is a little bit different. And in order to do your unit tests, you actually want to run those tests, those unit tests on the module, not just your code. And this is what the Rust SDK allows you to do. It basically lets you run unit and integration tests on individual and multiple modules at the basic Rust cargo test framework. It also gives you a REPL, basically a local availability, a local instance of the Marine VM. So you actually can run your modules locally and interact with them. And another way to just play with them, figure out test function signatures, and even test them manually. That was the Rust SDK. Now we also have, so for those of us who hate Rust, it has to be JavaScript or TypeScript. We also have Fluence JavaScript. And right now it provides everything necessary to create a peer that is able to connect to the network and through a relay node, and lets you turn interfaces, JavaScript interfaces into Aqua consumable interfaces. So basically, you get the same benefit, well, not the same benefit, but you get the same programming model and an execution model with Aqua, regardless of it being a WASM service or actually a JavaScript type node. Actually, it's TypeScript node. And we do this by making an Aqua virtual machine available. And so this runs in a browser, right? It could run via an Edge client, but it runs in the browser. The part that's missing is you can't run those WebAssembly IT modules in the browser just yet. However, we're working on a Marine runtime called WebMarine that's going to be available hopefully soon. I don't know, 2 months maybe. And then you have a full-fledged JavaScript TypeScript environment that lets you actually run Rust type services, WebAssembly services in the browser, which are not BindGen WASM, but WASM IT, which is super, super cool because it actually runs on the Rust nodes as well, and wherever you port the Marine runtime to. And that actually is I don't know, you have to dig in a little bit, you have to use it. It's unbelievable cool. And it gives you a lot of options, and it really, really helps you in the reuse of your resources. And by reuse, if you really think about sort of the different types of actors you have in this ecosystem, you could have one actor that's just focusing on operating nodes, Rust nodes, you know, peers. You could have an actor or actors that focus on creating services, which are then hosted by this other type of actors. And then you could have actors that build protocols and applications by reusing the already hosted services. So, I mean, you could be one person or one team could be all three actors, or it could be totally split into different identities and totally different business models, which gives you a large, powerful capability to really drive decentralization, cost savings, and any of the Web3 aspects you really want, which I presume is why you're here. Then we have Aqua. Aqua is a high-level language, and that really is, Aqua is what makes everything come together, work, and this is really, for the most part, particularly from a protocol and application development perspective, the entry point into the entire system. And so it's a high-level language. It's a compiler that takes the high-level language and turns it into an immediate representation. And it has command line interfaces, which actually gives you, as part of the library, a very small, thin client. So you can actually test your, or even run Aqua scripts right up from the command line without having to even build JavaScript or any other type of clients. Oh, now Aqua. Been talking about it. It's time we put the rubber to the road here and go from the academic to the practical. At the bottom, we have an Aqua excerpt. So assume we have a WebAssembly service, a greeting service that's out there somewhere on the network. And it's a fancy greeting service. It takes two parameters, a string and a Boolean. And basically, the Boolean determines whether we greet or say goodbye as that service, and the string is just basically the addressability of the greeting. So if the string is Gitcoin and the Boolean is true, our response would be hi Gitcoin. And if our Boolean is false, it would be bye Bitcoin, right? So it's just basically a real fancy hello world. We have the service out there. It's running on some node, on some peer, and it has a service ID, which we see here. So this line 1 and 2 is your binding. If you're coming from blockchain, for example, you can think of it as your API, right? And I mean, you don't have to come from blockchain, but if you're Solidity, you're really, really familiar with this kind of structure. And then lines 4 onward, this is actually your Aqua function. So you get your function signature on top, and it's greeting, the function name. And then we have our parameters. So we have the name and the greet, which actually correspond to that interface, right? And now we have the remaining two parameters, the node, which is the peer ID, it's a string, and the unique service ID, which is a string, which is our, in this particular case, our all we need for our addressability. And then that function returns another string, hello Gitcoin, or hi Gitcoin, or bye Gitcoin, right? Gitcoin. So now this is a really cool part. Now, if you've never done any any peer-to-peer programming or even lib peer-to-peer programming, then you haven't suffered enough to fully appreciate what I'm showing you here. But basically, what it allows you to do it basically, like, it's so simple. It basically says on this peer, where we have the address, the peer ID here, we instantiate our binding to the provided service ID. Okay. So now we have an instantiated service on whatever peer we specified here. That's it. This is ready to go. And now we execute for this binding, this particular function called greeting. And we provide it with the name and the greet parameters. And we collect that into a result. That's it. So what you're basically doing is you have a client. So if you go in the upper right, you have this client. And it could be a JavaScript client. It could be your CLI. It could be whatever. And you're flinging this particle now. The particle, simply stating, is that compiled piece here, those 8 lines, plus your data parameters, right? Your name, the type of Boolean, the node address, the peer ID, and the service ID. So we put all this together and we fling this out to this relay node. Let's just say we have a thin client, so we need a relay to actually get onto the network, and that's how we initiate our request. This is our request, and then the system takes care of you. The discovery inherent in the peer-to-peer network basically gets you to whatever node hosts that service we talked about, which is this node with this service, but the service has this service ID, and we call this. So the Aqua VM now executes through this compiled part. It knows we need to go here. It finds the service, basically makes sure that service is executed on the Marine virtual machine, and then we get the result back. And the result here going back is actually still on this node. This part here is on this node. So we're over here with the result. The relay in our case, basically, is just a pass-through to get connectivity. So we don't pay much attention to it. And then down here, we actually go back the result and hand it back to that client peer. So this is it. Now, yes, it's a little bit more work than writing a REST towards a REST endpoint, possibly. But if you start looking the verbiage in REST, whatever, it actually isn't that much more. The really cool part is that you're not stuck with location addressability like you are with REST or JSON RPC, which aside from all the decentralization benefits, actually is extremely helpful to resolve moved resources. So anytime a node changes for whatever reason IP address, so if you were to run a node on your home system, let's just say you have enough or an edge device, and you have a cycling IP address, it's a non-issue without ever having to go through a central DNS or decentralized DNS for that matter. It's part of the network topology fabric, how this discovery works. And this actually is super, super powerful. Let me see what we have here. Okay, no more questions. Does anybody have any questions right now here? I know I'm going fast, but I always run out of time. So, okay, well, if you have any, put them in chat or just speak up. So this is in a nutshell. This is Aqua, and as you can see, if you ever wanted to write a peer-to-peer application on your own, what you would have to do is you have to go take libp2p, which is a huge improvement over what you had a few years ago. So then you have to make decisions on what kind of network exchange, what kind of interaction data you want, what kind of gossip protocol, how you put security in. Everything in Fluence comes automatic with end-to-end encryption. It has all the key management. All this stuff is taken care of where you're already. So you really can just go and start build protocols and applications. And Aqua really abstracts. You don't have to deal with any of those low-end metal type programming chores, which are so far from where you usually want to be when you implement or want to implement the protocol or an application. Okay, you have a chat question here. Okay, so far so good. All right, so in order to make things even easier, Fluence provides a growing integration ecosystem. And one of the big integrations, or one of the first ones, which we really, really like, is IPFS. So how do you do this? And actually, I'll go through the code with you in a little bit. So I'm gonna go a little fast, Fluence IPFS, because we're gonna spend like probably 20 minutes on it. But basically, what we're doing is so you have this network of this peer-to-peer network of Fluence nodes. And I say Fluence nodes because right now the reference implementation is the only one, and that's Fluence. You can take it, you can fork it, you can make it John or Brian's or Can's peer-to-peer node, and that's cool as long as it as long as the interfaces and the node itself still adheres to the protocol and the specifications. So with the Fluence reference nodes right now, we make available IPFS node, an IPFS node as a sidecar. So when you actually look at our Docker container to deploy one of those Fluence nodes, reference nodes, IPFS is already included in it. And the cool part is that we provide you with all the tooling to actually program and interact with IPFS from Aqua. So as far as you as a protocol and application developer are concerned, there is no difference from a programming model between compute and data. And that actually is really, really cool. And at least I think so. And we'll get into that, as I said, like at the code level in a little bit. We do the same with Ceramic. Ceramics is a little bit different because it sits on top of IPFS, so you need multiple ways to access Ceramic. You can do part of it is through the HTTP API, part of it is through the CLI API. The interesting part with the Fluence integration is that it's actually happening at the file system level. So what we've done is we've said, I told you earlier that with the right permissions, service modules, WASM modules actually can go beyond the sandbox and utilize permissioned host resources, which includes the file system. So we created a file vault, if you will. Well, actually, that's what it's called. It's a file vault that's on the host, on the peer. And if you have put or get commands against IPFS, that's where the files go and come from. And then the web service, the WebAssembly module actually accesses or operates on the copy in the file system and put in the file system of the node it is hosted on. Sounds more complicated than it actually is, but that makes it extremely powerful and extremely effective and super, super fast, super low latency, especially since the IPFS nodes are sidecarred. Same thing with Ceramic. And then there are, we have a bunch of additional building blocks. So we have a bunch of Fluence examples. So it's, if you go to github.com/Fluence Labs/examples, there's a ton of examples for Aqua, for Marine, for everything. However, over the past year or so, we've had multiple hackathons, several with Gitcoin, which I thought went really well. And the community has really done some really, really cool things. So there's one that was working on NFTs. There has contracts, whatever. So if you need anything of that, you can go there. We had contributions with decentralized identities for authentications and general assigning services, which are both built on Ceramic. And that's really important if you want to do dynamic NFTs with dynamic data, or dynamic NFTs with data on, say, for example, Ceramic on a decentralized solution. So that basically governs what resources actually have access to the data representation of the NFT, so you can update it. And just since a few people seem to be newer than others, some of the cool things of dynamic NFTs is, for example, if you have a, I don't know if you're into sports, but if you have, I don't know, a baseball player card, if you will, as an NFT, you could keep updating that player's statistics. So if she hits, I don't know, as the player evolves, the metadata evolves with the NFT without ever having to remint the NFT. And that's obviously like huge. This is like super cool use case to really make NFTs super valuable beyond the art, straight art, but even living art actually uses dynamic NFTs. So it's a really cool use case. And then we have somebody who's still working on very complex Web3 projects, and they're actually using Ethereum and Elasticsearch adapters, which is super cool for indexing. So if that's something you want to look at, that's something you should look at. And then we have multiple Web3. So one of the interesting implementations were basically hackers took an existing Web3 library and exposed some or all of its interfaces to be used by Aqua. Why does it matter? It matters in the following. Well, it matters for a lot of instances, but one of the really important use cases, which you probably will encounter as you're hacking your way through the bounties, is signing services, off-chain signing services. In order to guard your key properly, so your private key properly, you need to run your own node. You don't want to run your own node for everything, but this is where Fluence JS node comes in. It could be super handy. And where you really just use it for signing services. So if that node goes offline, you're not particularly worried about it, unless, of course, you want to sign something. Not interactively, of course. Otherwise, you could just use any old wallet. And those two repos really cover that. And I think one of it is Ether.js. So you really get the whole signing workflow already ready for you to use in those repos. Okay, any questions here? Let me look at the chat. Okay, how is time handled? Are you worried about block time kind of time, or I'm talking to Sterling? What I don't quite understand the question or the concern. Okay, so we don't there isn't a transaction pool in the traditional blockchain sense. As you create as you create and execute that Aqua script, as I showed you here, actually, let's look at it here. As you create this, and you go from hop through hop through hop, you fundamentally create a temporal virtual private network, right? Because your services are addressable, and the lifetime, the span of this Aqua, it creates this virtual coverage of the network, the subnetwork. It's not really a subnetwork, but for you as a Aqua programmer and owner, it looks like a subnetwork. So ordering messages doesn't really matter. So unless you go into parallel, right? So everything is sequential until you hit a parallel fork. In the parallelization, ordering isn't happening per se. Whatever finishes first whatever sequence, you get the returns. This is how it gets, and then the state gets updated. So the state, regardless of how the messages come in or the compute comes in, is going, it doesn't matter. So it's up to you to design a workflow where this is acceptable. And this is where, when we looked at particles, it's where those conflict-free replication data structures comes in, because you have this eventual consistency, and the eventual consistency is not the eventually over the run of your Aqua script or the lifetime of your logic. It's actually over your service branch or your fork, like parallelization. Does that make it clearer? All right. Okay, cool. Happy trails. And when should you use Rust versus Aqua versus Fluence.js? Okay, so Aqua is you can't compare it. It's Aqua allows you to compose your service resources into a workflow. And so regardless of whether you use Rust or Fluence.js, the question is Rust versus Fluence.js. So with Rust, you literally write WebAssembly modules. With Fluence.js, you write JavaScript as you would async, for example, as you would always, and then you are able to expose those JavaScript or TypeScript interfaces as if they were WebAssembly modules, but they're not. And from an Aqua perspective, it doesn't really matter. The important part is that you have a virtual machine. Hey. Every time UPS comes at this time, I should know better than schedule my workshops for this time. So what matters is shut up. What matters is that hang on one second. Apologize. What matters is that WebAssembly modules are easily portable. You can run them just about in any environment. Whereas Fluence.js, it's fundamentally, it's a node structure. It's a much less fine-grained approach to resource capabilities than what you have with WebAssembly. And as I said, so in many respects, if you use Fluence.js and you expose, I don't know, 5 or 6 interfaces to be used by Aqua in conjunction with any other WebAssembly services, or not, it doesn't really matter. Aqua itself doesn't distinguish, as long as there's an Aqua VM available and the interfaces are processable. Your Fluence.js node, if you will, your client, is your sort of mega service, right? You can't slice it, dice it, and partially host it somewhere else. Whereas WebAssembly, you can. So the level of granularity is at the WebAssembly module. So when to do one or the other, if you want to have optimal reuse and granularity, particular fine-grained function level development is important to you, think Lambda, for example, then you probably want to use WebAssembly modules, which right now is only available in Rust. If you want, for example, to wrap a signing service and you have already a library like Ether.js, for example, and where the granularity is the library, it is that SDK, then, and you need a lot of control over it, then Fluence.js helps you to do this very, very effectively. So now we've taken some Rust libraries, like general ones, and ported them to WebAssembly, so you can do the same thing. However, some of the more particular Web3 libraries you can't easily port because the way they're built is that they're built from a transport layer up, and the transport layer is HTTP and in particular web services. So you have long-running connections, and that's really problematic to build into WebAssembly. And that's where the JavaScript client, the Fluence.js, comes in. The other thing is you have to think a little bit of security. On the network level and on the transaction level, everything is encrypted end to end. But what's the end? The end is the peer, not the service, right? So as the decryption is happening, it's happening at the peer level. So there's this level of exposure between the peer and the WebAssembly module that can be problematic. So if you have huge security concerns, just like with anything else, don't send your keys, right? Don't send your decryption keys. That's why a signing service, for example, a non-interactive signing service would be probably best, is best suited, and not probably, is best suited as running in your own node. And that's where Fluence.js comes in. And that's about it on that. And now I've gone like way too far. We got 7 minutes. I really wanted to show you some code, so now I'm like totally depressed. I'm even slower than usual. Let me show you something really quick.
Bernhard, I don't have a hard stop in 7 minutes, so we can go as long as you need to go.
Okay. Yeah, well, I'm sure it's Friday evening for people, so I don't want to keep people too long. But what I want to show you is IPFS integration. So, and the example I'm going to give you is the following. We are creating a WebAssembly module in Rust. That WebAssembly module is here. And basically what it does is a very simple WebAssembly module we're creating that allows you to calculate the file size of whatever file path you're giving it. That's it. So that illustrates sort of to a certain extent how fine-grained you can get. And if you look at the code real quick, so this markup here, this macro is basically, it's from Fluence. It's the marine markup. It's the marine macro, and it does a few things. It checks for types, and it makes sure that whatever is marked up and properly is actually exposed to the WebAssembly module interfaces. And if you look at it, so basically this is in JavaScript, this is a structure. In JavaScript, it would be an interface. This is how you do your files. So there's a little bit of Rust sugar in there in terms of doing a match statement instead of just doing a if else, if then else, but if else then. But fundamentally, if you've done any JavaScript or some Python or whatever, you look at it, it's like, oh yeah, I get it. Yes, you're gonna be starting a little bit if you haven't done it before in Rust, but as you see, it's like, it's very, very simple, because everything, if you look at the function signature, it's passed by value. Everything is passed by value. So we have this service, and I already compiled it. And when you compile it, it basically creates this WebAssembly module. And I told you we have a REPL. And if we look into this REPL and we look at the interfaces, we get exactly the WebAssembly module public interfaces we specified here, right? Our size result, our write result, and then those are our function. Calculate the file size and write the file. And you can interact with that. We'll skip over that. But so we have this module now. This is sitting on my laptop here. And what we really want to do is we want to deploy that WebAssembly module as a service onto some node out there in the network. So let's just see. Okay. So we built a little interface, a demo interface for us to look at. And basically what it lets us do is it lets us pick a Fluence IPFS combo and just any relay. I just gonna pick this one. And we're connecting this. So we're now, this browser now is the client. That client is connected to this particular peer in the network. And if you look, this is part of the Fluence test network. So it's one of those peers that are out there that comprises one of the test networks. That's it. So, and with that node, we get the IP address, the RPC address of the IPFS. So what we want to do in order to deploy that WebAssembly module as a service to any one node out there, or any node, or all the nodes, whichever ones you want to do, we want to first save it onto IPFS. And the way we do it now, I'm lazy. I'm using the IPFS desktop client for the Mac. And we take this IP, this multi-address for the IPFS node, and here we have it. It's up and running. So now I have this clean slate IPFS client, and what I want to do is, of course, I want to move or copy that WebAssembly module onto IPFS. And this is why I said I'm lazy. I just drag it rather than use the IPFS CLI to put it on there. And so now we have this file on there, and this is the CID. This is the content addressable ID. This we use on IPFS, right? Because that's how IPFS gets its censorship resistance, failover, many other things. Is it's not location addressable either. It's content addressable. So now we go back to our handy little React client browser, and we update the CID, which is for that process file. And now we deploy the service. So this is all happening on the back. So now, basically, let me just go through the whole thing. So we get it. So now we have a service out there that can calculate file sizes, right? So now we want, again, on IPFS, what we want to do is we want to actually have a file we calculate the size for. We could use that one, but it's kind of lame. So let's use, let's not use that. Go away. Let's upload another file. So we cargo 431 bytes, right? We got the CID here. So this is addressable on the IPFS network now, or on that particular node. And so all we have to do is our service, if you recall from before, all we have to somehow get the file path to it. And we do that by deploying it to the network. So boom, let's calculate the size. And here it is, 431 bytes, which is, yes, it checks out. So where's all this magic? Here's the magic. I'll show you the magic. It's not magic. The magic is actually Aqua. So in Aqua, we now want to deploy the service. This is our, let me make this a little bit bigger. This is our Aqua function to deploy the service. And if you look at the signature, just like before, it takes the node, or here we have a relay, which is the peer ID, which we had up here, right? When we connected, we got it. We want the CID of the file, which we did when we put it on the IPFS node. We got the content ID. We need the IPFS multi-address, which, remember, we got it when we because we know that it's a sidecar node to the Fluence nodes. It's very simple. We provide that. And then this is a callback function. We call it an error, but it's a callback function. So basically it logs back to the React client or your Fluence client. And it returns, and then the function returns optionally a service ID, where the service ID is just an alias for string. So here we declare the variable. And then basically, just like before, this is how simple it is. We say on this node, on this particular relay, we want to execute an IPFS get call. And if that call, and for that, all we need is the multi-address and the content identifier. And if that process is successful, we now calculate all these hashes to get the blueprint and to get the service ID, and add blueprint and is up here. And I told you before that we wrote a lot of those services already. And let me go here. So you got in the Aqua book on the libraries, it shows you the API we already created that's available on every Rust reference node. And actually the Fluence.js as well, to interact through Aqua with IPFS. So this is our get and set functions, including you can do timeout, put, get from, all that stuff. And this is exactly what we're using here. So all of this is also written in Aqua. So basically, you know, orchestrating or composing with Aqua across two different networks, peer-to-peer networks as it happens to be, and using this very, very simple but extremely powerful abstraction on top of libp2p fundamentally, because now you're actually mingling function addressability with content addressability. And neither one is location-based. Neither one uses IP, which is the key to most of the Web3 benefits. Obviously, I'm really into it, as you can tell, so I get excited about it. If our result is a failure, we have a coroutine that initiates that callback to the client and basically says it failed. Our service ID, it's basically an empty string, which we have here. This is why it was optional. And in the client, you obviously have to catch the error, and off you go. Once we have all that in place, we deployed it. I showed you how to where was it? Oh yeah, how to basically now we just can put in different file CIDs, and we just keep calculating the result. And this is what we're doing here. And basically all this part, again, it's just the function signature, just like before. You need your CID, multi-address, service ID. Again, we have some callbacks here, and your node ID, which is the relay. And then again, very simple. On this relay, pick up the content. If we get the content successfully, we now call our service. And this is, remember when I showed you the first little example about the greeting where we had the service binding? Well, here we're doing it right up front, and this is the binding. We're binding the service, which is, I think, here, right here. This was the interface with those two functions, but if you look at the REPL, it's quite there. And we bind them to that service ID, which we got from here. So this is the instantiation. And then we just go through it like before. And again, it's literally, if you take the all the markup, the comments out, it's 10 lines, and you compose a fully distributed peer-to-peer hosted service across two peer-to-peer networks, the Fluence network and IPFS. It could not be any simpler. And obviously, the more complex your workflow gets, the more complex it gets. But still, the addressability issue that usually haunts peer-to-peer developers is totally abstracted for you and taken care of by Aqua. And then our last one is actually how to remove service, because you want to be a good citizen and not leave a bunch of garbage on those nodes. So you just delete it, and in order to delete it, you use another built-in service. This is already provided for you, and you just basically remove that service from the host. Okay, chat. I'm almost done. I'll just gonna go quickly go over the bounties, and then I'm available for more questions. So we have 4 bounties. One is a beginner's bounty, an intermediate bounty, and an advanced bounty. I'll get to the best use of Fluence in a minute. Those 3 bounties actually build on each other. And I just want to be very, very clear. We want you to, if you going for the advanced bounty, we want you to go for the beginner's bounty. We want you to go for the intermediate bounty, and we want you to keep building on it. And if your submissions are good enough, we are happy. We are excited. We are thrilled to pay you out for each one of those bounties. There is no exclusivity. So just build up and get into it. And obviously there's where it's easier, it's more. There are more, and then so 5 times 500, and then 1 times 1,000, 1 times 2,000. So the beginner's bounty. Either use the JavaScript or the Marine SDK and create integrations to custodial NFT wallets, OpenSea and Rarible. The reason I chose this theme for this hackathon is the following. There's a lot of centralization happening around decentralized Web3 resources, including NFTs. And just recently, it was made public that it's very, very easy, particularly through OpenSea, to obtain NFT holders' IP addresses, which then can be exploited for any other, for a large number of exploits. So if you look at the thread from beginners to intermediate to advanced bounties, it basically gets you to build your own wallet. Custodial, non-custodial, I don't even care at this point, to basically create, mint, read, display, and buy, sell NFTs. So, of course, on the beginner's bounty, really just provide some integrations into those custodial wallets and APIs of those 2 marketplaces. If you feel you should use a different one, let me know. I'm sure we can work something out. And just basically find, fetch, and display NFTs. Because another interesting part is, for example, in some of those marketplaces, if you're not longer listed, you can't find most of your wallets can't find your NFT asset any longer because it's no longer available through the API. And a lot of the wallets are actually all, lazy. I can't blame them. And they use the API instead of actually going out and looking and indexing on the blockchain level. So this is so on the beginner's bounty, there's some leeway, and I believe you'll build some really cool stuff. The intermediate bounty is basically build a super wallet to across 2 marketplaces. So this is sort of a multi-marketplace approach, and the advanced one is to really blow it out and build the full wallet. In addition, so this is 5 times 500, 1 times 1,000, 1 times 2,000. In addition, we have best use of Fluence and Aqua in your dApp. So if you already have an idea of something, you want to build something, or you already done something and it has some components that need to be centralized or could benefit from off-chain, or you actually really look at Aqua as okay, I can replace thousands of lines of code with just a few, that's for you. And I got a few examples for there. So, decentralized NFT creation, storage solutions, for example, NFT storage from IPFS, which is plain IPFS, create multi-source decentralized exchange price oracles, for example, including for NFTs or trade books, order books, whatever you want to do, enable off-chain DAOs, anything. I mean, those are just examples. Whatever you have in your mind for your dApp, this is, and there's room for Fluence and Aqua, go for it. We'd be happy to support you and look forward to your submission. For additional resources, we have a website. We have 2 websites. Another spelling. God. The repo is at GitHub. It's the second website. It's on GitHub, Fluence Labs. You got Discord, Telegram, Twitter. You can also, if you hit us up in Discord, for example, we can set you up to book a time with me or any of the core developers we are global, so we almost cover 24/7, and it doesn't matter where you are. We'll more likely to find a really good time for you. And we are hiring both in technical and non-technical capacities. So if Web3 is your stick and or your jam, and you like what I saw and you have something to bring to the table, reach out. We're definitely looking. And that's it from my end. I'm sorry it took longer. I really didn't want to, but that's how it goes. And if you have any questions,
Yeah, I don't have any questions, and I don't see any in the chat. I wanted to thank you for your time, Bernhard. I'm totally fine with it going over. It's always super informative, and I think a lot of people got a lot from it. So thank you for that. I'm going to probably drop the Fluence Discord. I think Anna might have dropped it in our Discord as well, but if not, I'll drop that in the Selling Point Hackathon underneath where we were talking about this workshop too. So with that, I'll just say thank you so much, everyone, for joining us today. And take a look at the bounties. If you're in our Discord, I linked the bounties that are Fluence's bounties there. I think I can find it real quick and throw it in the chat so it's easier for y'all. Hold on. Yeah. Yeah, let's see. Yes, I just threw it in the chat. But with that, take a look and get started, and happy hacking. All right, everyone, have a great weekend.
Have a great weekend. Thanks for being here. Thanks for having me. Thank you.
Bye.
All right.